about the two main types or main methods of making ATP to power or sustain contractions. Now we can begin to look at the different types of muscles, the classification of skeletal muscle. So we can classify skeletal muscle based on two things. First is the velocity of the contraction. How fast are those contractions? And on that basis, we can think about fast muscles versus slow muscles. The other mechanism or method for classifying muscle is what is its primary source of ATP production? What is its primary source of generating energy? And on that basis, we can think about muscles as being oxidative if they mainly rely on oxidative phosphorylation, or glycolytic if they mainly rely on anaerobic glycolysis. So let's talk about the speed first. So the difference in speed of contraction, we have fast twitch fibers and we have slow twitch fibers. This is going to be the first name of the muscle. So whenever we call a muscle or type a muscle, it's going to have a first name and it's going to have a second name or last name. And so the first name is based on its speed of contraction. So that is going to be dependent on the rate of myosin ATPase activity. How fast is that myosin ATPase on the myosin head? Does it hydrolyze the ATP very quickly? Or does it hydrolyze the ATP very slowly? And so on that basis, that is going to determine how fast are the cross-bridge cycles. So if we have a fast fiber, that means the myosin heads on those fibers can generate ATP hydrolysis very quickly, and they can endure cross-bridge cycling very quickly as well. If we have a slow twitch fiber, the myosin head on those fibers takes a longer time to hydrolyze the ATP. Therefore, cross-bridge cycling is going to be even slower on those slow twitch fibers. Okay, so fast fibers have a fast rate of myosin ATPase activity. Slow fibers have a slow rate of myosin ATPase activity. All right, let's see what else is true between fast and slow fibers. So the other thing is that fast fibers are going to relax more rapidly as well. They're going to contract more quickly, but they're going to relax more quickly as well. And that is because of another feature, which is the calcium ATPase activity. So remember we said that the calcium ATPase is what is responsible for pumping calcium back into the SR. So by way of putting that calcium back into the SR, we're going to help the muscle to relax. We're going to remove the calcium from troponin. We're going to cover up the myosin binding sites on actin, and we're going to help the muscle to cease contraction, in other words, relax. So if I have calcium ATPase pumps that are faster and they can clear the cytoplasm of that calcium much more quickly, that is going to allow the muscle to relax much faster. And so it's going to actually allow the muscle to contract more quickly in terms of stimulating the next upcoming contraction. So fast fibers not only contract faster, they relax faster as well. Slow fibers, on the other hand, are going to contract more slowly, but they're also going to take a longer time to relax. And if you think about the contraction of a slow fiber, it's going to be sustained for about 10 times the duration that a fast fiber will sustain contractions. Okay, so much more slow in terms of their rate of contraction and relaxation. Let's compare a few different muscle types. And we want to think about not only their rate of contraction, we want to also think about their duration of contraction, right? How long they sustain or keep that contraction going. And then we want to add here, we want to think about the function that that muscle is bringing about. So let's start with the extraocular muscles. And we mentioned this earlier, the extraocular muscles are really fine, delicate muscles. So they have a short duration of contraction. They only stay contracted for about 7 to 8 milliseconds. So it's a very short twitch. The gastrocnemius muscle, on the other hand, is going to sustain contractions for longer. It's going to sustain contractions for about 40 milliseconds, okay? And then the soleus muscle. So the soleus muscle is going to be one of our postural muscles. It's going to be muscles that are deep to the gastrocnemius, and these are muscles in our calves. So these are going to help us stay standing and walking for long durations of time. So these muscles are going to be slow twitch fibers. They're going to not only keep contractions going for a longer time, but they're going to take a long time to relax as well. And so the soleus muscle will have a contraction duration for about 90 milliseconds, which is comparatively much longer than the extraocular muscles. Okay, so the duration of contraction also speaks to what type of function that muscle is going to bring about. Extraocular muscles are really delicate in their movement, right? Think about actions like blinking, which are fairly, low in terms of the amount of power that's needed for that muscle, and sustainability that's needed for that muscle, whereas the soleus needs more power and more sustainability to keep that contraction going. Okay. So now that we have talked about the methods of ATP generation, and we have talked about the way that we classify muscles based on the first name being the speed, the second name of the muscle is going to be due to its primary mode of ATP production. And when I say primary here, muscles are going to generate ATP by both of these mechanisms, okay? But what is the main source? What is the majority of the ATP that muscle generates? What mechanism is making the most of the ATP? And so that can be either glycolytic or oxidative. So a glycolytic fiber is going to primarily rely on anaerobic glycolysis. It's going to have fewer mitochondria. And the reason is because mitochondria is the site of oxidative phosphorylation. So if we are not relying on oxidative phosphorylation, we don't need as many mitochondria. It's going to have a lot of glycolytic enzymes. And the reason is because if our main source is anaerobic glycolysis, we need to have lots of glycolytic enzymes. If you remember us talking about cellular respiration back in chapter 3, we talked about glycolysis as being the series of enzymatic reactions that resulted in going from glucose to pyruvate. So all of those enzymes that are needed to carry out those enzymatic reactions, we're going to need to have lots of those glycolytic enzymes in order to generate ATP if our main source is anaerobic glycolysis. We're going to have lots of glycogen stores, right? We're not going to need as much oxygen, and that is because anaerobic glycolysis does not rely on oxygen. So we're not going to need as much oxygen. We're not going to have as small a diameter. So the diameter of the muscle fiber is basically determining how much distance that oxygen has to diffuse across. So if we have large diameter fibers, that is because we don't need oxygen to be able to diffuse across these fibers. If we had small diameter fibers, that would be more so for oxidative fibers, which need to have a small diffusion barrier for oxygen to get across into the muscle. Okay, and then the last feature here for anaerobic or glycolytic fibers is that they're going to be quick to fatigue. And that is all due to the fact that there is lactic acid buildup. So they're going to power contraction, they're going to generate a small amount of ATP. They're going to do so very quickly. And the benefit is that they're going to do so in the absence of oxygen. The drawback or the price to pay is that they're going to be quick to fatigue because of the lactic acid buildup. All right. In terms of looking at our cross section here, these large fibers that appear white are referred to as our glycolytic fibers. Okay. Notice they have a bigger diameter. Notice they all appear white. So the reason that they appear white is because they don't have a lot of myoglobin. They don't have a lot of mitochondria. They don't have a lot of myoglobin, so they don't appear red or dark in this staining pattern because they are not reliant on oxidative phosphorylation. All right, so large fiber diameter appearing white, using little oxygen, but generating lots of glycogen stores and these needing lots of glycolytic enzymes, and that will be our glycolytic fibers. Let's turn our attention to the oxidative fibers. So these are going to have lots of mitochondria, right? They're going to need to have a lot of mitochondria in order to generate ATP by way of oxidative phosphorylation. They're going to have a lot of myoglobin. Myoglobin is the protein in our muscle where we have the storage of that mitochondria. And so for that reason, these fibers are going to appear red, okay, these darker appearing fibers. They're going to have a smaller diameter. So notice that these fibers are much smaller than these larger fibers. They're going to have lots of capillaries. So notice in between here, we can see these little dark striations. These are actually the capillaries that are surrounding the darker fibers. And again, just to explain why we need to have more capillaries and a smaller diameter is because we need to have oxygen diffusing from these capillary beds into these muscle fibers because we need oxygen to power oxidative phosphorylation. Okay, it's a requirement for oxidative phosphorylation. So we need to lower or shorten the diffusion barrier across which that oxygen has to move in order to get that oxygen into the muscle. And then lastly, they're going to be resistant to fatigue because they do not have the lactic acid buildup. It's going to be more sustainable. There's going to be more oxygen coming in. And so we're going to be able to sustain contractions for longer periods of time and keep those contractions going. Okay. We are going to move into the 3 types next time we meet, but I want to end off on this note. I want to just draw 2 parallels. So think about your oxidative phosphorylation. Think about a long distance runner, right? When we think about those long distance runners in the Olympics or even marathon runners, they are going to have a lot of this type of muscle. That is not to say that they won't have glycolytic fibers, but the majority of their muscles, by training, by definition, will be trained to rely on oxidative phosphorylation so that they can run for long periods of time. As long as they keep their rate of breathing pretty steady and pretty constant, they are going to condition their muscles to rely on oxidative phosphorylation. Alternatively, when we think about glycolytic fibers, think about your bodybuilder, right? Think about your power lifter who is, again, conditioning their muscles, but in a different way, conditioning their muscles to rely on anaerobic glycolysis. This is why bodybuilders, their muscles get really big and bulky because the fibers are allowed to get so big because they no longer have to rely on the diffusion barrier because they don't have as much of a requirement for oxygen. So align your glycolytic fibers with your big, bulky body lifter, all right? And align your oxidative fibers with your lean, long-distance runner, which has smaller muscles, smaller fiber diameters, because they need to have that small diffusion barrier to get oxygen into the muscles.